So on to some supplemental stuff. This is chapter 5, vector spaces, Hilbert spaces, and the L2 space from a textbook on real analysis that I co-authored in about 2005. The chapter 5 stuff is it's predominantly on Hilbert spaces, and so fits the conversation for functional analysis. Section 5.1 is groups, fields, and vector spaces. So the plan is to set the stage for exploring Hilbert spaces by reviewing some linear algebra material. We'll have mostly review concepts, except that we'll see some new ideas about bases. And we're going to work in a somewhat more general setting in terms of vector spaces here than you do in sophomore linear algebra. Here we'll take the field of scalars simply to be some field, not necessarily the real numbers or the complex numbers, but just some field. So in that direction of defining a field, first we'll define a group. A group is a set of elements, G, along with a mapping called a binary operation. We'll represent it with a star. We won't dwell on this very long. By binary operation, we mean it takes ordered pairs of elements of set G and associates them with another element of set G. We impose the requirements that there exists an element E in set G such that for all G, lowercase g, and group capital G, we have E star G equals G star E equals G. Of course, this is called the identity element of the group with respect to the binary operation, star. Next, we require for any element, lowercase g, in group G, that there exists a unique element H, such that G star H equals H star G equals E, the identity element defined in part 1. Element H is called the inverse of G, and it's denoted H equals G inverse. We require associativity of the binary operation for all G, H, and J in the group. G star, the quantity H star J, equals G star H, quantity star J. So we didn't change the order, we simply associated things differently. So we're requiring an associative binary operation for which there's an identity element and for which any given element there's an inverse element. We'll denote the group with these angle brackets, G with binary operation star. If in addition we do have commutativity, G star H equals H star G, then the group is called an abelian group or commutative group. And a subgroup of a given group is simply a subset of the set of elements, which forms a group itself under the binary operation star. Some examples, somewhat relevant to us. Under addition, taking addition as the binary operation, the integers mod n form a group, the integers themselves form a group, the rational numbers form a group, the real numbers form a group, the complex numbers form a group. All of these, arguably in a common setting, they're all subgroups of the complex numbers under addition, say. Rn under addition, Cn under addition, where we're taking n tuples of real numbers or n tuples of complex numbers, and we're adding them component-wise. Those also are examples of groups. Kind of an important example with an eye towards defining what a vector space is. So with that equipment, we can define a field. Fields can be defined a number of different ways. The approach we're taking here will be to skip over rings and go straight to fields. Talk about a field as a set of elements F, along with two mappings, two binary operations, denoted addition and multiplication, addition with a plus sign, multiplication with a little dot, such that addition maps ordered pairs of the field into the field. So does multiplication. In other words, they're binary operations, as I said. And we're requiring that under addition, we get an abelian group, a commutative group. The identity will denote a 0. The 0 is ultimately be where we get our scalars from, the 0 scalar, the additive identity in the field F. And we require that the field F, the set of elements, except for the additive identity, form an abelian group under multiplication. Even in this rather abstract setting, there's no division by 0. There's no multiplicative inverse of 0, even in the field setting. But what we've picked up with all these abelian comments is commutativity with respect to both binary operations. Associativity is buried in this abelian group stuff as well. We have identities, both additive and multiplicative, and we must have inverses, both additive and multiplicative, except for the additive identity. The identity element under multiplication is denoted with a 1. So we have 0 and 1 in any field. Z2 is the world's smallest field. We'll mention some fields here shortly. 1 is sometimes referred to as unity. We'll denote the field as F in angle brackets with the additive binary operation and the multiplicative binary operation, again, mostly in passing. A subfield of a given field, similarly to subgroup, is a subset of the field for which the subset forms a field under the two binary operations of addition and multiplication. Closure becomes a concern with subgroups and subfields. Some examples of fields are Z sub p, the integers mod p, where p is prime. By the way, p has to be prime to guarantee the existence of multiplicative inverses. If I take composite numbers and do addition and multiplication mod a composite number, we won't have multiplicative inverses, so that's why the prime condition is there. The rationals under usual addition and multiplication form a field. It's not a complete field. It's an ordered field, though. The greater than, less than applies on the rational numbers, but the rational numbers aren't complete in the topological sense. Cauchy sequences of rational numbers do not converge necessarily to a rational number. So there's one example of a field. By the way, it's an ordered field, but not a complete field. The reals under addition and multiplication form a field, maybe your favorite field, your most commonly dealt with field, probably in a setting of vector spaces. The reals are ordered with greater than and less than, and they're complete. Cauchy sequences of real numbers converge, if you want to take that as a definition of completeness. So here we have a complete ordered field. In fact, the real numbers are the complete ordered field. That's the very definition of the real numbers. There's only one complete ordered field, that can be proven. And that's what the real numbers are. The complex numbers under addition and multiplication also form a field. Not ordered, but it has a nicer algebraic property of being algebraically closed. An n-degree polynomial has up to multiplicity n roots in this setting. Not so in this setting. The real numbers are not algebraically complete. They're topologically complete. The complex numbers are topologically complete and algebraically complete. So place to be, in my opinion, is the complex numbers. The only structure you lose from here to here is the fact that the reals are ordered with a greater than, less than, and the complex numbers don't have such an ordering on them. All right, so we'll define a vector space over a field. The majority of our applications, that field will be real numbers. We might run into the complex numbers a little bit, but not so much. But for vector spaces, we'll define a vector space over a field. So vector space over field F, the elements of F are called scalars, is a set V of elements called vectors that satisfy the following conditions. A mapping called addition, defined or denoted with a plus sign, is the binary operation on the vectors. You take an ordered pair of vectors and produce another vector. So there's a closureness to this. We require the vectors under addition to form an abelian group. So in this, there's the implication of a zero vector. Again, we'll denote the vectors in these notes with boldface fonts throughout these Hong Wang Gardner supplements. That'll be the notation, is boldface fonts for vectors and not boldface for scalars. So we'll have that distinction visually. Implicit in this is also additive inverses of vectors. For any given vector, there's another vector that can be added to that vector in such a way as to produce the zero vector. The group part will imply that. We also have a mapping from ordered pairs, first entry in an ordered pair being a scalar from field F, and the second being a vector from set V. And we map this into the vectors. This is called scalar multiplication, and we require the scalar multiplication to satisfy the following for all scalars A and B and all vectors U and V. Say that correctly, for all scalars A and B in scalar field F and all vectors U and V in this set of vectors capital V. We require distribution properties. What we're describing here is the interaction between vector addition and scalar multiplication. Scalar A times vector sum U plus V is required to equal scalar A times vector U plus scalar A times vector V. That is, we have distribution of scalar multiplication over vector addition. Here's the scalar multiplication right here, and there's the vector addition in the title of that property. Part C, we require scalar A plus scalar B times vector V to be scalar A times vector V plus scalar B times vector V. That is, we have distribution of scalar multiplication over scalar addition. Right here between the scalars and the vectors, that's where the scalar multiplication is. And here's the addition related to the addition of two scalars in the scalar addition part of the title of that. We have an associativity between scalar multiplication and the multiplication of scalars. That is, A times B times vector V is this required to be the same as A times B times vector V. The scalar multiplication is here between this scalar and vector V, and there's also some scalar multiplication right here between scalar B and vector V. And there's another one between scalar A and vector B times V. And there's this multiplication, and didn't highlight very well. Between A and B, we have multiplication represented with a little dot. Yeah, that's the multiplication of scalars in the scalar field F. So we require this so-called associativity of scalar multiplication. The multiplicative identity scalar times any vector V is required to equal vector V. And our notation of boldface and not boldface works well in this statement. Scalar 0, the additive identity in field F, times vector V is required to equal the 0 vector for all vectors V. So there's the definition of a vector space over a field F of scalars. Some examples. Familiar and maybe not so familiar around the end. The rationals, Qn, n-dimensional rational vector space, where we take as the vectors n tuples of rational numbers. And we do scalar multiplication and vector addition component-wise. These you're used to. Another example is Rn. So what we have here with the rationals is always the components are rational. That'll form a vector space over the rationals, where the scalar field is the rationals. And it behaves quite similarly algebraically to the reals, Rn. Your favorite vector space, Rn, where we take n tuples of real numbers, and we do the scalar multiplication and vector addition the same way you do in sophomore linear algebra, do it component-wise. There's an example of a vector space over a different scalar field, this time the reals. We could replace real numbers with complex numbers and look at n tuples of complex numbers. That also gives us a vector space. Possibly you touched on that in sophomore linear algebra. Probably not, because you're busy doing other things, but The vector space behavior of all three of these is fairly similar. They're different algebraically in certain senses. The complex numbers are certainly different from the real numbers, and in topological senses as well. The rationals are not complete, and the reals and the complex numbers are topologically complete. And we'll primarily consider, in finite dimensions, we'll primarily consider Rn and Cn. We could generalize that idea and simply take Fn. Take n tuples of field elements, where F is some field. Do your scalar multiplication component-wise and do your vector addition component-wise, just like you do in Rn. And that'll form rather a general example of a vector space over scalar field F. And here's something that's if you're new to this functional analysis stuff, something that's a little more unusual. The space little L2 of R. What we're doing there is we're taking infinite tuples, I might call it. We're taking sequences of real numbers, R1, R2, and so forth, so that it is countable. Sequences of real numbers for which the sum from 1 to infinity of R sub I squared is finite. So these are square summable sequences of real numbers. They form a linear space, a vector space called L2, little L2 of R. And we'll do the usual scalar multiplication, we'll do the usual vector addition, and those actually form a vector space. Now there's a lot more details to sweat over on this little L2 space. Are you sure? If we add two of these sequences component-wise, the sum will be square summable as well? It is. It's not a real minor feat to establish that, but there's more things to worry about when we've passed over to this L2 space. It's an example of an infinite dimensional vector space, a very interesting infinite dimensional vector space, it turns out. And we could do a similar L2 type thing, except for using complex numbers. Now we'd have to take the moduli, or the absolute value of those complex numbers, squared, and require square summability of these things versus straight up the R sub i's before. And in that case, we'll produce L2 with complex scalars, usual vector addition, usual scalar multiplication. And indeed, it really is closed under vector addition, it turns out. So loads and loads of definitions here. Next, we're trying to get to the idea of the dimension of a space. So we have to go through basis and dependence, linear dependence, and spans and so forth. Suppose we have a vector space over scalar field F. A linear combination of vectors v1 through v sub n is a sum of the form scalar times first vector plus scalar times second vector, blah, 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 plus scalar times the nth vector, where the f1 through f sub n's are scalars from field F. So usual definition of linear combination, only slightly more exotic since our scalars are coming from a field instead of, say, the real numbers. A set of vectors, v1 through v sub n, is said to be linearly independent if we take a linear combination of those vectors and get from that linear combination the zero vector. That only occurs when all the scalars are zero. Usual definition of linear independence, common definition of linear independence. Of course, in the scalar field, we have a concept of a zero there. It's the additive identity in the field. The span of a set of vectors, v1 through v sub n, notice we're only taking finite sets here. We can liberate ourselves somewhat from that. Actually, we can liberate ourselves quite a bit from that, but we won't be able to liberate ourselves a huge amount, and we'll have to consider always finite linear combinations as long as we're in these fields F. Now, if we're in the real numbers, we can do some things with limits and possibly talk about series. But for now, everything is finite linear combinations, and so we're dealing with finite sets. The span of a finite set of vectors is simply the set of all linear combinations of that collection of vectors. We could have a bigger set of vectors and still talk about the span. It'd have to be talked about in terms of finite linear combinations. at this stage only makes sense to take a finite linear combination of vectors. There is no series of vectors, not yet. We're headed there, though. So the span of V1 through V sub n is simply all possible linear combinations over all possible choices for the coefficients, the F1 through F sub n here. With that defined, a basis of a vector space is a linearly independent spanning set of the vector space. The spanning tells you there's enough vectors there to write everything in the vector space as a linear combination. And the linear independence tells you it's an efficient set. There's not any extra vectors there. There's not any unnecessary vectors. So always think of a basis as a linearly independent spanning set. You might not always define it like that, but ultimately that's the idea behind a basis. You'll always end up there, ultimately. A vector space is finite dimensional if it has a basis of finite cardinality. So what we're going to look at in this video is finite dimensional vector spaces. Okay, to talk about dimension per se, notice we didn't define dimension just then. We defined finite dimensional. We didn't define dimension of a vector space. To do so, we need, basically, we need some linear algebra. Lemma 5.1.1 says, consider the homogeneous system of equations as given in a usual sophomore linear algebra style and notation. Notice it's homogeneous. We've got zeros entirely on the right-hand sides of these equations. The coefficients, a sub ij, and the unknowns, the x sub k's, we're taking to be field elements. Otherwise, if they're real numbers, I can just appeal to sophomore level linear algebra. We'll do sophomore linear algebra type manipulations, and we can still do that because we're taking the scalars from a field. The claim here is, if n is greater than m, then the system has a non-trivial solution. N is the number of unknowns, m is the number of equations. So if you have more unknowns than equations in a homogeneous system, there exists a non-trivial solution. That is a solution x1 through x sub n, where not all of those unknowns are zero. Sometimes this is called an underdetermined system of equations. So let's go through a proof of that. And I'm going to give an inductive proof of this. So we'll prove the result by induction on the number of equations m. So first, suppose we have m equals 1 equation, and we have more than one unknown. So we have an equation of the form a11 x1 plus a12 x2 and so forth, a1 n x sub n equals 0, all these being scalars from a field. If all of these coefficients are 0, if a sub 1j is 0 for all j given here, then we can just take all the x's to be 1, and we've got a solution because all the coefficients are 0. So we're done there. If one of the coefficients is not 0, we need to consider that, and that's what's on the next slide. If some coefficient, say a sub 1j star, is non-zero, then we have a non-trivial solution given as follows. We're going to take all the coefficients, all of the unknowns to be 1, except for the unknown in the j starth position. So what we're doing is assigning 1 to all of the x sub k's except for the j starth position. Let's go back and look at the system again. Right. This is the system, this single equation we're looking at. So we're taking 1, 1, 1, 1, 1, 1, except for in that j star position where we have a non-zero coefficient for sure. Maybe some of the others are non-zero, maybe not. In that j star position, we're taking the unknown x sub j star, x sub k when k equals j star to be this thing. Now, all those ones, except in the j star position, when you deal with the arithmetic there, you'll get a11 times 1 plus a12 times 1, blah, 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 plus a1n times 1. You'll simply get A11 through A1n, except that you skipped the A sub 1 J star position. You skipped the J star position. So we'll just write them all out and subtract that one off. That's what you get from inserting all the 1s for K not equal to J star. Now we're going to take X sub J star to be this thing. Remember the coefficient there is A sub 1 J star. A sub 1 J star we're assuming is non-zero, so it has a multiplicative inverse. So we're going to take A sub 1 J star and multiply it by X sub J star, this thing here. In so doing, we've got A sub 1 J star times A sub 1 J star inverse. That's gone. You're left with a negative A1 plus A12 and so forth. So what we get in the J star position is exactly the negative of what we get from all of the other terms. It's just arithmetic done in a field. It's a little involved. It's a little messy because of all the double subscripts and so forth. But simply solve for X sub J star in terms of the other coefficients when we set all of the other unknowns equal to 1. And it'll produce this. So that gives us a non-trivial solution, and the result holds when m equals 1 and n is greater than m. We're doing induction on m. This is the base case. So one equation, we get a non-trivial solution. Next, suppose the induction hypothesis, the result holds for a system of m minus 1 equations and n minus 1 greater than m minus 1 unknowns. So we want to show that it also holds when we have m equations and the appropriate number of unknowns. If in such a system, all of the coefficients, the a sub ij's, will introduce the system of equations on the next page again. If all of the a sub j's are 0, if all the coefficients are 0, we can take all of the unknowns to be 1, and we get a non-trivial solution. And it's an uninteresting system of equations. So what we're left with is a case where some a sub ij is non-zero, kind of similar to what we did up here. If some a sub I star j star is non-zero, consider the following. Okay, this is going to look pretty messy, but it's really just matrix manipulation style. Manipulation of the system of equations. We didn't create a matrix. We're still looking at the systems of equations. But what we're doing is taking the original system of equations and eliminating the variable x sub j star from all of the equations by subtracting from the first equation a sub I star j star inverse, which by the way exists because that a sub I star j star is not 0, times a sub 1 j star. So we're taking this times the ith equation and subtracting. Here we're taking a sub I star j star inverse times a sub 2 j star times the ith equation and subtracting. What that produces, trust me on some of the arithmetic, is first term, second term, the x2 term, blah, 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 all of similar form. Till we get to the j star coefficient, and here we get a1 j star minus a sub I star j star inverse, a sub 1 j star, a sub I star j star inverse, I'm sorry, a sub I star j star. We get this in its inverse. Okay, we got commutivity in this field, so those are gone. We'll have a sub 1 j star minus a sub 1 j star. That coefficient of xj star in the first equation will be 0. That's the manipulation we did. Hey, the j star, x sub j star coefficient in the second system of equations similarly will be 0. All right, here's the thing and the thing inverse, and these two are the same, slightly different. We had first subscript of 1 on these two in the first equation. First subscript is 2 here, and so forth. And it cascades through the system like that. Here's the last equation, so modified. And again, this and its inverse, and we get subtraction of this from its We get these two being additive inverses, producing a zero coefficient of xj star. So what we've really done is just eliminated xj star from all of the system of equations. All right, so we actually lost an equation there. The j star equation has become 0 equals 0. The coefficient of xj star is 0 in all of those, as just observed. In the j star equation, you'll actually see that we get the equation 0 equals 0. So we lost that equation. Well, excellent. We got one less equation then. And we still have a homogeneous system of equations, and we still got more variables than unknowns. So what we'll do is consider the new system of equations that results with m-1 equations and n-1 variables. We lost the j star equation, and we've removed the x of j star unknown. So both of those are reduced by 1. Still got a homogeneous system. Hey, the induction hypothesis tells you there exists a non-trivial solution to that system of equations. So we can find a non-trivial, not all 0, x1 through x sub n, except for x of j star. Well, if you can find all these other ones, then you can find x of j star in terms of these other ones. So we get exactly this for xj star, and altogether we got a non-trivial solution in this new case. So we found x1 through x sub n except for x of j star, and then we can go back to the original j star equation and solve for x of j star in terms of those others. So we found a non-trivial solution to the new system of equations, and by induction, this result holds for all m greater than 1, greater than or equal to 1, and all n strictly greater than m. Holds whenever you have a homogeneous system of equations with more unknowns than equations. Okay, back to the notes, and we went through all of that stuff, not unfamiliar stuff, really. It's the exact same kind of thing you do in sophomore linear algebra, except you probably use real numbers instead of field elements. And we went through that so that we can deal with Theorem 5.1.1. Let VF be a vector space with bases V1 through V sub n and another basis W1 through W sub n. And the claim is n equals m. In other words, if we have a finite dimensional vector space, which this must be because it has a basis with only m elements, any two bases are the same cardinality. And of course, we're headed to defining dimension with that. So next, take the vector space. Suppose the v's and the w's both form bases for this vector space. We're going to work under the assumption that n is greater than m. We're going to get a contradiction, drawing the conclusion that n is less than or equal to m. And the procedure we're going to use can be, we can interchange the roles of the two bases and get that inequality reversed. And that's how we'll draw the conclusion that n equals m. So suppose n is greater than m. Since the v's are a basis, then for some coefficients, we can write all the w's as linear combinations of the v's. They're a basis, they're a spanning set, and these are vectors in the vector space. So W1 through Wn, each of those is a linear combination of the v's. Take these things to be the coefficients. So now we want to think systems of equations so we can use that lemma. So let x1 through x sub n be unknown elements of f, quote unquote, so I can lead this into a system of equations. Now we're going to take a linear combination of the w's using the x1 through x sub n as coefficients. There's some currently unknown elements of field f. Well, if I take a linear combination of the w's, and I can represent the w's in terms of the v's, then we know what we get from this. We're going to take vector w1 multiplied by x1, take vector w2 multiplied by x2, and so forth. Do that substitute for all these W's, these resulting things here, which produces quite a massive equation, and then collect together the V1 terms, the V2 terms, and the V sub m terms. What were we going to get? X1 times this, X2 times this, blah, 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 X sub n times this. So when we collect together the V1s, we'll have X1, A11, X1, A12, through X1, A1n, which is exactly what's written here. There's the coefficient of the V's, and we get similar things for the other linear combinations. X1, X2 through X sub n, X1, X2 through X sub n in terms of those others. So all we've done is a substitution and collected things together in terms of getting a linear combination of the V's on the right-hand side. All right, consider the system of equations. What we're doing is taking the coefficient of V1, setting it equal to 0. Coefficient of V2, setting it equal to 0. Coefficient of V3, V sub m is the last one, setting it equal to 0. So I want to consider this system of equations in the field. So we've shifted from vectors to systems of equations. We have assumed that n is greater than m, n is strictly greater than m. That was our setup. So making that assumption, we've got more unknowns than we have equations. So there's x1 through x sub n, a non-trivial solution to this system of equations by the lemma that we just did. Non-trivial solution, x1 through x sub n, not all of them 0, that satisfies this system of equations. This is the coefficient of V1, coefficient of V2, the coefficient of V sub n. They're all zeros. So we've got a linear combination of the V's with coefficients all 0. That'd be the 0 vector. So what this means is there's x1 through x sub n, such that we get a linear combination of the W's set equal to the 0 vector. And not all of these x sub k's are 0. It's a non-trivial solution. That's where the lemma comes in. But that means we've got a linear combination of the W's, not all coefficients being 0, that produces a 0 vector. That means this is a linearly dependent set. It can't be a linearly dependent set. It's a basis. It was given to be a basis, which is a linearly independent spanning set. That's a contradiction, since the W's form a basis. Well, then the assumption that n is greater than m must be false. And we must, in fact, have n is less than or equal to m. Do it all over again. Similarly, we can draw the conclusions, a little cut off on the slide here, that m is less than or equal to n. Simply interchange the roles of the two bases. We wrote the W's as a linear combination of the V's under the assumption that n is greater than m. Reverse their roles. Write the V's as a linear combination of the W's and assume m is greater than n. The same logic will cascade through. You'll draw the conclusion that m is less than or equal to n as stated here. Those two inequalities show us that n and m are the same, and so those two bases have the same number of elements in them. Drawing the conclusion, back to the notes, any two bases for a finite dimensional vector space have the same cardinality. That cardinality is called the dimension of the space. So we can formally define this now. If vector space VF is finite dimensional vector space, then the dimension of the vector space is the cardinality of a basis. We're about to classify finite dimensional vector spaces. Funny little story. When we go to infinite dimensions, we'll have a similar result to this theorem 5.1.1. We'll show any two bases are of the same cardinality, even for arbitrary vector spaces. All right, so we've got our eye short term on finite dimensional vector spaces. The next definition defines an isomorphism between two vector spaces. So take two vector spaces, VF and WF. They both have to be from the same, over the same scalar field. So they have the same scalars, or else this won't make any sense. So isomorphism between vector spaces is only defined when the scalar fields are the same. These two vector spaces are said to be isomorphic if there's a one-to-one and onto mapping phi from the set of vectors in one space to the set of vectors in the other, such that for all scalars, f and f prime, and all vectors v and v prime in vector space V, we have phi of the linear combination fv plus f prime v prime equals f phi of v plus f prime phi of v prime. So we're saying an isomorphism is a one-to-one and onto, a bijection that preserves linear combinations. An isomorphism between mathematical structures is always a bijection that preserves structure. In a graph theory graph, that structure is adjacency. In a vector space, it's linear combinations. In a group, it's the binary operation. In a field, it's the two binary operations. So we're talking vector spaces. The structure is linear combinations. So an isomorphism is a bijection which preserves linear combinations by definition. So with that little bit of background, we're prepared to completely classify finite dimensional vector spaces. So this next result tells us what's a finite dimensional vector space, as I like to say it. What's it look like? We're giving a classification of finite dimensional vector spaces. To be a little more mathematically precise, the result tells us up to isomorphism, what an n-dimensional vector space looks like or what it is. I find this so impressive, I'm going to refer to it as the fundamental theorem of finite dimensional vector spaces. This term first appears in that book I co-authored in 2005. You Google this and you're likely simply to find stuff that I've got posted out there online. But it's very reasonable, in my opinion, my humble opinion, to call this a fundamental theorem of finite dimensional vector spaces. And it foreshadows the fact that there's a fundamental theorem of infinite dimensional vector spaces, a much longer story, but we'll encounter that before we're done. So theorem 5.1.2, the fundamental theorem of finite dimensional vector spaces says, if VF is an n-dimensional vector space, then VF is isomorphic to Fn, which we'll denote as V star F, where the vectors in Fn are simply n-tuples of field elements, just like you do in Rn. Scalar multiplication, vector addition are dealt with component-wise. All that makes sense because we're dealing with a field here in which addition and multiplication are both defined and well behaved. So let's look at a proof of that. Okay, so claim is isomorphism between n-dimensional vector space VF and this particular vector space Fn, from which we can draw the conclusion that any two n-dimensional vector spaces are isomorphic. They're both isomorphic to this thing. Okay, we've assumed VF is n-dimensional, so it has a basis with n vectors in it. Let's call them V1 through V sub n. And let's define phi, a mapping from V to V star as follows. We'll take an element of V. What's it look like? It's some linear combination of these because these form a basis of vector space V. So take a vector, an arbitrary element of set V, write it as a linear combination of the basis elements using the scalars. When you apply phi to that element of vector space V, we're going to define the mapping simply to produce the n-tuple that uses the coefficients. So pick these coefficients off, put them in an n-tuple. And that is a vector in V star. There's the definition of the mapping. We just need to make sure it's one-to-one, it's onto, it's a bijection, and that it preserves linear combinations. Surprisingly easy with the equipment we currently have. V1 through V sub n, it's a linearly independent set. That gives us the one-to-oneness. Linearly independent implies we get a unique representation of this vector So whatever vector it is that's represented over here is uniquely determined by these coefficients. The vector determines the coefficients, I should say, and those coefficients then determine what we get on this side. So you put different vectors in, you get different n tuples out. You get the same n tuple out, you must have put the same vector in. So the one-to-oneness follows from linear independence, and the onto-ness follows from the fact that V1 through V sub n is a spanning set. You pick any n tuple over here, and that will be associated with some vector back over here, some vector in V. In fact, all vectors are dealt with in this way as well, and that's how we get the onto-ness. So one-to-one and onto, we just need to make sure it's linear. This mapping phi is linear, so take two scalars, f and f prime, two vectors, v and v prime, and let's apply phi to that. So take phi of fv plus f prime v prime. Well, we know v can be written as a linear combination of the basis vectors, v1, v2, oops, a little typo there. I should read v sub n, not f sub n, as a vector. And we know that v prime can similarly be written as a linear combination of the v's. Let's use f primes for the coefficients there. So we're taking v represented like this, and v prime represented like this. So we're simply taking representations with respect to the bases. All right, phi is going to be applied to that. So first, I know how phi behaves in terms of the basis vectors. So let's take the f coefficient here, distribute it, the f prime coefficient here, distribute it. Let's collect together the v1 terms, collect together the v2 terms, and collect together, so forth, the v sub n terms. All right, up here, we're going to have f times f1 times v1. Over here, we're going to have f prime times f1 prime v1. Collect together those v1 terms. That gives us a coefficient of f1 plus f prime, f1 prime, and a similar pattern throughout the rest of them. So here we're applying phi to a linear combination of the basis vectors, v1 through v sub n. What does phi do to that linear combination? It creates an n tuple with the coefficients as the components of the n tuple. First component would be this coefficient, f1 prime plus f prime, f1 prime. Second coefficient, and so forth. Again, same pattern, this time with the components of an n tuple instead of the coefficients of a linear combination. The phi takes us from linear combinations to tuples and components. How do you deal with adding these tuples? Do it component-wise. Well, we've got some f's plus some f primes in each of the components. So we'll just break that up into a sum of two n tuples. We get the f's in this n tuple and the f primes in this n tuple. Sure enough, add component-wise, it'll take you to the previous thing, so a legitimate operation. There's an f in each of these components. You can bring it out front. That's how scalar multiplication works in the V star vector space. We got f primes over here, same, f primes in each of the components here. We can bring the f prime out front. Same idea, it's a definition of how we deal with scalar multiplication. Hey, the tuple f1 through f sub n is by definition phi of the linear combination, f1 v1 plus f2 v2 through f sub n v sub n. So this tuple is phi of this linear combination. That's how we define phi. This n tuple of primes is phi of this linear combination, with the coefficients being the primed f's. But that's what v and v prime were. V was the linear combination with the f coefficients, v prime linear combination with the f prime coefficients. So this linear combination is simply v. This linear combination here is simply v prime. So we've shown phi of the linear combination fv plus f prime v prime equals equals the linear combination phi of v plus f prime phi of v prime. That is, phi of the linear combination is the linear combination of the phis, as I like to say. So phi really is linear. It's a bijection, and that's what an isomorphism is. So these two vector spaces are isomorphic. Returning to the notes, that means any two n-dimensional vector spaces over scalar field F are isomorphic to each other because they're both isomorphic to this vector space, where the vectors are simply n-tuples. So in sophomore linear algebra, that's why you're always dealing with n-tuples of real numbers. If you're in finite dimensions and the scalars are real, that's what the vectors are going to look like. Hopefully in sophomore linear algebra, you were exposed to the idea that this is commonly what's going to happen, but don't get too hung up on it. There's places out there where vectors are more exotic, and that's where we're going ultimately with this stuff. All right, so we know by the fundamental theorem of finite dimensional vector spaces, we know what an n-dimensional vector space looks like. We've got it classified up to isomorphism. How about we look at certain transformations of vector spaces? We want to look at linear transformations on vector spaces. In sophomore linear algebra, linear transformations were represented by matrices of real numbers, because everything was a real number, it seems, in sophomore linear algebra. I bet that holds here too. I bet linear transformations here are represented by matrices. I guess matrices of scalars. They'll be field elements in this setting. So it'll be a behavior quite similar to what you saw in linear algebra. So definition, a transformation mapping one vector space, V to another, W, both over the same scalar field, call the transformation T, is a linear transformation, a word I've already batted around quite a bit. If for all vectors, V and V prime in vector space V, and for all scalars, F and F prime, we have the transformation of the linear combination as the linear combination of the transformations, that kind of behavior we had with an isomorphism. So usual definition of a linear transformation, what we're going to show soon. I guess we need a definition of standard basis first. We're going to show we can represent linear transformations using matrices. First, we need to discuss bases and pick a standard basis. The standard basis for Fn is kind of the ijk's of n-dimensional space where the scalars come from F. So we'll take a 1 followed by all zeros, 0, 1 followed by zeros, a bunch of zeros, a 1 followed by a bunch of zeros, until we get all zeros followed by a single 1. So we get these n different basis vectors with a 1 in the first position, the second position, blah, 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 and the last position, the nth position. We'll represent commonly the standard basis vectors with e's, e1 through e sub n. Notice if v is any vector in f sub n, then v can be written as first component of v times e1 plus second component of v times e2, and so forth. And we can represent this vector v as the n-tuple. So the components of the n-tuple determine the coefficients with respect to the standard basis. Sometimes this is called the standard basis coordinate vector, or the coordinate vector with respect to this basis, by which we mean they're the coefficients necessary in a linear combination in that basis to produce vector v. All right, next result is if T is a linear transformation from n-dimensional vector space VF to m-dimensional vector space WF, same scalar field, then T is equivalent to the action of an m by n matrix, A sub T, that maps Fn into Fm. So we've got a few moving parts here. We've got the vectors in vector space V, and we've got their coordinate vectors in Fn. And we've got vectors in W and their coordinate vectors in Fm. So let's go through the proof of that. We'll wrap this video up with this proof. Let V be in vector space V and consider the representation of this vector with respect to the standard basis vectors E1 through E sub n. So we'll write V as some linear combination of those vectors and associate vector V. So we're defining this n-tuple, associating vector V with this element of Fn. It's simply the coefficients over here, treated as components of an n-tuple, if you like. So we're taking the coefficients and making them elements of an n-tuple. Then if we apply the transformation to V, T of V, that is T of this linear combination. We said this is a representation of V with respect to the standard basis vectors. T is a linear transformation, so we can do our linearity thing, get the coefficients outside, and this usual behavior over the vector addition. So we can express T of V as a linear combination of T of E1, T of E2, through T of E sub n. These vectors, T of E sub I, they're elements of W. Suppose that with respect to the standard basis for WF, okay, that would be, we said it was m-dimensional. Yeah, m-dimensional. So that would be the m standard basis vectors in this vector space, consisting mostly of zeros and the occasional one. Suppose we have the representation of T of E sub I as A1I, A2I through A sub mi. That is, T of E sub I, an element of vector space W, is A sub 1I times the first standard basis vector of this vector space, plus A sub 2I times the second standard basis vector, and so forth up to the mth and last standard basis vector in this space. That is, this is the coordinate vector of this vector in vector space W with respect to the standard basis for vector space W. So we'll define this matrix A sub t using those coefficients. And like I said, we'll bounce back and forth a little bit. Here we've got A1, let's consider I equals 1. Say A1, 1, A2, 1 through A sub m1. That's the first column. So these are those coefficients that we would get associated with T of E sub 1. Coefficients we'd have associated with T of E sub 2 through the coefficients we'd have associated with T of E sub n. Now, the claim is that this matrix behaves on the coordinate vector for vector V, coordinate vector with respect to the standard basis in Fn, the same way the transformation affects vector V. That is what we get out as T of V written in coordinate vector with respect to the standard basis for Fm. So let's try to unwind some of that. So suppose we take vector V. We'll have to treat it as a column vector to make sense out of the matrix multiplication, but we'll take this vector V1 through V sub n. Write it as a column vector over here on the right, and then do our row times column matrix multiplication stuff. In doing that, let's keep an eye on the first position. We'd have a V sub 1, then a V sub 2 through a V sub n. Let's concentrate on kind of I equals 1 again. So when you do the multiplication, we'll do row times column. What gets together is A11 and V1. Second row, first column, A21 and V1 get together. There's that product. A31 times V sub 1. Down through A sub M1 times V sub 1. So it's each of these that gets multiplied by V1. It's each of these that gets multiplied by V2 and so forth. So what's happening to V1? It gets multiplied by all these things here. Now if we go back again and look at what's going on here, we've got V1 times T of E1. Well, T of E1, this vector written with respect to the standard basis for vector space W, would be this tuple here. If we take V1 times this with I equals 1, we get V1 times A11, V1 times A21, blah, 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 V1 times A sub M1. And that's precisely the same products we were talking about when we were doing first row, first column, second row, first column, blah, blah, blah. So we get the transformation producing the same result, the matrix producing the same result as a linear transformation. But it's complicated by the fact that we have to go through these standard basis representations, or some basis. We need ordered bases, and it's most general. It's easiest done with a standard basis. But to make the matrix behave like the linear transformation, we need tuples. And so that's why we have to go to treatments of Fn and Fm. And you know this vector space V, being n-dimensional, is isomorphic to Fn. This vector space W, being dimension m, is isomorphic to Fn. So you know those isomorphisms exist. The use of matrices requires you weaving through something with an ordered basis to produce the n tuples. So the matrix multiplication actually makes sense. You didn't quite have this problem in sophomore linear algebra because you were in Rn and you treated the vectors as n tuples of real numbers the whole time. Here we've possibly got something more exotic, and we use standard basis representations to get the n tuples. And that'll do for now. What we'll look at next is some ideas about bases. So we'll come back and finish up this supplemental section in the next video and look at Hamel bases and Chowder bases. And I will see you there shortly. Have a nice day.